right, so I want to cover Betz Limit because this is well, it's pretty cool the way it works out. There's a little bit of sticky math in here, and I'll just kind of warn you ahead of time. I'm gonna skip through the last little icky bits of it, but what I really want to show you is kind of the overall derivation of Betz Limit. So just bear with me here a little bit. Pretty cool the way the thing works out. So Betz law, Wikipedia has a really good write-up on it, but hopefully what I'll do is sort of show you how Albert Betz idealized the maximum efficiency that a wind turbine can have. So we've talked a little bit about the efficiencies of photovoltaics. We talked about the efficiencies of heat engines. As it turns out, in a wind turbine, you can't do any better than 59.3%. And the primary reason for that is that, what goes in must come out. So A1 is more or less the area of the wind that's coming into the system, and A2 is the area of the wind that's going out. And what this is telling us is that you can't really make the wind slow all the way down. Something's got to trickle out somewhere. It's gonna leak. If you could, if the wind just bounced off your turbine instead of blowing through it, maybe it would go up. But this is some pretty cool mathematics the way it works out. So what he does, and I'll just follow along here with my own notes. See if I can't kind of get both things on the screen at the same time. What he does is, and again, I mentioned conservation of mass, so here it is. This is m dot equals rho A1 V1 equals rho S V equals rho A2 V2. And let's look at that for just a second. We'll do a dimensional analysis on it. So mass dot is just mass per unit time. It's how much chunk of matter, how big a chunk of matter is flowing through your turbine. Equals the density, so that's mass per unit volume, which is length cubed, times area, which is length squared, times velocity, which is length divided by time. So we can see that this length cubed cancels with this length squared times length, and we're just left with the mass flow rate equals the density times the area times the velocity. Makes sense. If you've got a substance that's more dense, an area that's bigger, or if it's going faster, you've got a higher mass flow rate. And so these three chunks, 1, 2, 3, simply refer to these three spaces, 1, 2, 3, or 1, nothing, 2, however you want to think about it. So whatever goes into the system passes through it and then leaves. So conservation of mass, that's where we start. Pretty simple. Okay, now we just get on to Newton's second law, F equals ma. So I'll just follow along with that. So F equals ma. Now acceleration is the same as the change in velocity over the change in time. The little trick that he uses here is just to, instead of saying that the velocity is changing with time, it's the mass that's changing with time, like how much mass is flowing through the thing. So he writes it as m dot, again our little friend m dot, times delta v, big change in velocity. So we already know that the mass flow rate equals rho s v. And now the change in velocity, well, that's just what the velocity was going in minus the velocity going out. Pretty cool. Okay, so we've taken Newton's second law and more or less combined it with this this conservation of mass equation. So this is the force pushing on the blade. Now we get to look at the turbine in yet another way. Power and work. I think we know what that is. This is where it gets a little bit trickier, but bear with me. We know that if we're going to change the energy of something, we're going to push on it. So dE is just the change. So D is the change in energy. Well, how do you change the energy of something? Well, you push it with some force through some distance dx. The reason for using the d's is so we can just sort of make it arbitrarily small, right? You've got your blade sitting here. It's going to move a little bit. So that's just that little tiny bit, however small you want to make it, is your dx. And what's pushing on it? Well, the force. Where's the force coming from? The wind. Okay. So any change in energy of this blade is a result of it being pushed through some little distance dx. Now we also know that power equals a change in energy with respect to time. So we'll write that again as F. So we've divided the whole equation by time. So it's F times dx dt equals F dot V. And we kind of knew this already. We knew that power is the product of force times velocity. Where's the velocity? Well, it's just the velocity of the wind moving through the turbine. Okay. Now, we also know if we substitute the force that we just calculated above, let's go grab that again. The force calculated above was rho SV V1 minus V2. I think I can maybe get that on the page here. Yeah, so now power equals rho S. The V becomes a V squared because force was rho Vs, so V squared, V1 minus V2. And power, so that's one expression for power. Another one is that the, so I'll just call this power 1, or power, I'll just call it power 1. The other one I'll just call power 2. Another way to look at power is the change in energy. So that's just going to be 1/2 times m. So this is just our kinetic energy equation, times m dot v1 squared minus v2 squared. And so what he's done next is, and you see the little m dot here, he's gone all the way back up to the top, taken our expression for m dot, and done a substitution. And so we've got P2 equals 1/2 rho S V V1 squared minus V2 squared. All right, so now we have two independent expressions for power. This is expression 1, this is expression 2. One's based on force or work, and the other one's based on energy. And so all we do next is combine the two together. So equating these two expressions, and this is where it gets a little bit long, so I'll give myself a little more space up here. And I'll say that 1/2 rho s v times v1 squared minus v2 squared equals rho s v squared v1 minus v2. And so, again, this is where I'm going to kind of skip through and hurry a little bit, but it says, examining them and equating them yields an interesting result. So after, scratching your head for a while and solving this thing, what we end up with what we end up with is actually kind of funny and trivial when you think about it. We've got, so 1/2 v1 squared minus v2 squared equals 1/2 v1 minus v2, v1 plus v2 equals v times v1 minus v2. And now we've sort of gotten rid of the size of the turbine, we've gotten rid of the density of the air, we're just dealing with velocities, just velocities. It's kind of nice. So after all this pain and suffering of algebra, we've finally got the thing simplified, which is the whole point. And now we just end up with is that v equals 1/2 v1 plus v2. Well, what does that look like? It's just an average. It just means that somewhere between the fast wind coming out and the fast wind coming in and the slow wind going out, there's an average velocity. So there's now from there, and this is the part where if you get back down in here and try to look for power, there's a little bit of calculus to figure out where the maximum power is. There's a little derivative that goes on. As it turns out, it's a pretty clean result. You end up with 16 divided by 27. It's just that's the magic number that pops out. 16 divided by 27. So let's just do that. 1/6 divided by 2/7 equals 59.2. So that is Betz limit right at the top of that curve, and that's the most efficient you could ever have a wind turbine. So there it is. Kind of cool, kind of fun. And I think that really shows the power of the mathematics, because it doesn't even matter what shape the thing is. We've looked at all these funky shapes, and people are like, oh, if you do this and try that, well, sorry, this is Newtonian physics here, first law of thermodynamics, you're not going to be able to argue with it, that's the best you're going to do. So if some guy comes up and says, hey, I got this Betz limit thing, you got to question that a little bit. Where's the hidden fan, or where's the hidden motor in your turbine that's giving you all this extra energy that you're claiming? Okay, so that's kind of fun. Let's see what's next here. Okay, I think we can keep going with the figures for a little bit. Okay, so any turbine is going to have some kind of initial friction. So there's, obviously in physics there's this thing known as static friction. So if my hand or object, or this could be the wind turbine sitting on its bearings, is just doing nothing, the wind starts blowing, it's going to take a little bit of extra velocity to get the thing going. That's what's known as the cut-in wind speed. So all of a sudden, it's not spinning at all, and then it gets enough, and it moves from the static coefficient of friction, which is always higher than the dynamic coefficient of friction. It gets up and moving, and there you go. So now we can start to see that V cubed kick in. So when we did our power equation last time, we know that power is a function of velocity cubed. At some point, though, the turbine just can't spin any faster. And so if we go back, at some point it reaches its mechanical limit where it's just simply going to fly apart. You can't spin a technology infinitely fast without something breaking. So the thing to keep in mind is this: power equals tau omega. Okay, so the thing is spinning faster and faster and faster, but there's not really any more torque on it. So think about sitting on your bicycle and you're pedaling, and now you get on a big downhill and you keep trying to pedal. I mean, your legs might be spinning really fast, but you can't really push. It's the same thing with the wind turbine. It's going so dang fast that there's not any additional torque. It more or less flatlines at its rated power, and at some point you're like, okay, enough's enough, something's going to fly apart, it's time to feather it or just shut it down. So there's a limit. Now, that said, every wind site is going to be a little bit different. What we're looking at here is a typical wind speed frequency. It's given in meters per second, and it says that some of the time you're going to have winds that blow at 1 meter per second. It's more likely to see wind speeds of 2, et cetera, et cetera. When the wind is blowing. And what I think might not be a bad idea for a graph like this would be to show how much time you're not getting any wind at all. So to be able to rate this against some, standard for when the wind's not actually blowing. But then what this is also saying, that very rarely are you getting wind speeds of 19 meters per second. 40, 45 miles per hour, and that seems pretty reasonable. So you take this, and this will affect your decision as to what type of wind technology to use. Whether it's, if it's relatively low, you're going to use something that's high torque. If you've got higher wind speeds, you're going to use something that's low torque, high speed. Okay, so from this chart, we can now see that then we can just flip back and forth with these. You're like, oh great, I'm getting a lot of wind at 5 meters per second, 6 meters per second. If I go back and I look at my power, I'm like, well, I got a lot of wind here, but I'm not getting a whole lot of power there, right? So if we click forward a couple here, we can see that, well, if, when we get to 11 meters per second, 10 meters per second, 12 meters per second, there's a lot more power, because that is more or less multiplying, we more or less multiplied this curve by this curve. And so big numbers times small numbers are equivalent to small numbers times big numbers, and that's more or less what we're doing. And we got a lot of speed here, but not much power. Not as much speed here, but less frequency. But as it turns out, for this particular technology, 10, 11 meters per second are sort of your money makers. You're going to make a lot of power out here at 19, 20, 21, but the wind just doesn't blow that frequently, so you don't get a whole lot of juice there. Okay, so that's what these three curves. So these three curves are meant to be interpreted together. Okay. Now, so you've got your technology figured out. We know the physics of wind turbine blades, and now you got to go out and decide where you're going to put it. This is looking around Western Europe. And what we see is that there's the nice dark blue stuff. Up around here is where we're getting class 5 winds. So, and this is all done at 50 meters above ground. Sheltered terrain. We can see that the numbers are a little, and it's difficult to see down here, but for sheltered terrain, class 5 wind is greater than 6 meters per second. Open plains, you got to get to 7.5. At the seacoast, 8.5. In the open sea, 9. And on hills and ridges, from this side, I think this must be a hill and ridge area. I should know my Spanish and French topology, geology a little bit better than I do, but anyway, that's what these colors mean. So the bluer the better, the red is second best, and then these sort of light blue bands are where you're going to see not a whole lot of wind activity. Okay. There's a little bit on wind flow simulation and computer models. I've done a little bit of that with some students in the past. Fun and necessary. Okay, we'll keep going here. Okay. Now, the next question is, you've got your turbine technology picked out, you've got your spot picked out, but what are the drawbacks? So the environmental impacts that are listed in the textbook are noise. If this thing's whipping away near your house at night, it's going to affect your sleep. Electromagnetic interference, so anytime you've got a magnet spinning inside an enclosure, there will be some waves coming off. And since it's not always spinning at the same frequency, the interference can happen at different bands. So also something to consider whether you're messing with CB, radio, cell phone bandwidths or not. Aviation-related issues, so you wouldn't put one of these right on the end of a airport runway, big target. Wildlife, mainly birds. I've also heard that the acoustic waves emitted by some turbines can mess with bat sonar, bat aviation, so there's another wildlife issue. Public attitudes and planning, some people just don't want to look at a wind turbine, so those are all environmental. Now, here are the classifications of different noises. So what we're looking at, the thing to focus on, the wind farm at 300 meters, so this is more or less your wind farm. Here's 300 meters away. It's given in the book as 35 to 40 decibels. So a quiet bedroom is at 20 decibels, and just above that is a car driving past. So if you are 350 meters away from a wind farm, you're noisier than a quiet bedroom, but you're quieter than a car driving past at 50 miles an hour 100 meters away. So, living near the interstate, for example. Obviously, the further away you get from the turbine, the less noise. And I don't know, it doesn't say exactly what the decibel level is. Yeah, maybe it does. I think what we're seeing here is the turbine itself, if you're standing right next to it, it's going to be in the 40 to 50 range. And so I think if we just sort of marched in here all the way to the root, we're probably going to hit 50 decibels. I was trying to figure out, starting out here at 36, 39, 42, 44, 45. I think by the time you're at the base, you're probably right around that 50. And I don't know, like right now, I'm trying to compete with the heating in the room. So, and it'd be nice to have a little decibel meter with me, but I'm guessing we're probably hearing 60, 70 decibels there from that machine. We've all driven a car, we know what that's like, industrial noise, pneumatic drill, et cetera. So, quieter than a stereo, okay? Yeah. And I think there's just a couple more things to cover in this section. Chapter 7, Part 3. Oh yeah, so this is showing if you have a radio signal. I mean, it's a big enough of an object that it could, in fact, scramble or mess with radio signals where you might have a transmitter and a receiver. They're trying to talk to each other over the straight path. The radio waves are not like laser beams. I mean, they do span out more or less in a circular or spherical fashion. So some of that could come over here and cause an issue with your receiver. So not only do you not want your airplane flying into a wind turbine, the UK ministry says that it could affect radar. So in a similar way that it's messing with these radio transmissions, could be your radar.
It shouldn't be that low anyway.
Well, it's true.
I guess harvesting planes.
Yeah.
They're not really using the radar either.
Well, I mean, no, but it could be that, the turbine is there and giving a false signal, the radar bounces off of that, and, depending on, the details of how that signal is reflected could scramble or confuse the radar, like, because of the rate at which the turbine is spinning and interacting with the radio frequencies. There's a thing on wind turbines. It says, so far the worst location for bird strikes has been the Altamont Pass in California, where some raptor species have been killed. This is apart from bird strikes on wind turbines in Tarifa and Navarra in Spain. This raptor mortality does not seem to have been duplicated elsewhere. So it might have been due to special circumstances. It says the American Bird Conservancy reports that 100,000 to 440,000 bird collisions happen per year. This seems like a lot to me. I mean, I don't know, 4 to 5 million with towers, 10 to 150 million with power lines. So you've already got, that issue. 10 to 380 million with roads and vehicles. 31 million with lights, and another with glass, like 1 billion birds hitting glass. Now, so what these statistics aren't showing though is how many birds hit these objects per unit area, because there just aren't as many wind turbines as there are big buildings. So it would be interesting, is there something special about a wind turbine that draws a bird to it, just like, a moth flying toward the light? I don't know.
From what I've heard, because that's a big thing in California,
Yeah.
turbines, the lift and the drag, from behind.
Yep.
The birds like to
Ride that.
ride it.
Huh.
And then, something happens, they
Gotcha.
lose their lift or something, and
Gotcha.
then they get sucked right into a turbine.
So the bird's there kind of surfing the wind turbine wave, and then it gets rolled and smashed into interesting, okay.
And then, the noise of it is what attracts the bats.
Yeah,
So,
yeah.
again, it's still, but I don't think it's so many per turbine. But we're killing more birds with our cars than,
Yeah, cars really do a number on them. All right, so we'll take a break there, and then we'll get into economics, commercial development. There's small scale, communities, a few other things, offshore. Yeah, so let's just take a quick break.